Okay, so section 5.1. So this is integrals, general integrals, and general antiderivatives. And so we made our list. I'm going to go ahead. I'll go ahead and rewrite it just so that we can refer to it. So we have the following integration rules. The first thing is notation. This means take the antiderivative up. It's an instruction. The next thing you should ask yourself is with respect to what? That means you need to have this part. So these two pieces together tell you take the antiderivative with respect to x. Just like when we would say d dx is the instruction to say take the derivative with respect to x. So you need both parts. If I have this, any power, I know the answer will be raise the power by 1, divide by, or multiply by the reciprocal if it's a fraction. That's easier. Plus c, because any infinite number of numbers would work, and I don't know what they are yet. We're going to talk today in class about how to find out what fits there. We have e to the x goes to e to the x, and 1 over x dx, or more importantly, dx over x is ln absolute value of x plus c. Okay, so let's look at a couple more examples. So we have started with, we did some examples from the recap, so that's good. So now let's look at adding some layers. So we've talked about the first thing you need to do is recognize the difference between powers and logs. So we know that this is a log, but this is a power. Okay, so, and we know that because if we try and rewrite that, we'll get something that's nonsensical. So this is a log, and this is a power. We've also talked about the fact that if you have anything like this, the first thing you need to do is rewrite it. It is a power, but you have to rewrite it to get it into the right form. That's the same with derivatives. So square roots, all of that work the same way. Then we have some other things that we used to do with derivatives as well. So here is one. X to the 4th minus 8x cubed all over x squared dx. There is no reverse quotient rule. There is no reverse product rule. So I can't even think about that. But when I look at this, and this is something we also did with derivatives sometimes, is there a way to rewrite this that's a little bit easier to deal with? The answer is yes, I can break it apart. X to the 4th over x squared and x cubed over x squared. So let's go ahead and do that. So x to the 4th, and you don't have to do this intermediate step if you can do the canceling correctly. Remember your parentheses, dx. So all I've done here is just break apart this fraction, right? You can break apart the numerator as long as the denominator stays the same. Okay, and so then we just have the integral of x to the 4th over x squared minus 8x. Now those are really easy derivatives to do. Okay, they're all power rules. We love power rules. So I think I'm starting to write low on the board. Let me see if I can get one more line in. So the antiderivative of x squared, it's a power. So we'll take the exponent and raise it by 1, and then divide by. So there's a 1 there, so 1 divided by 3. 8x. Deal with the variable first. This is x to the 1, so we raise the power by 1, x squared, and divide by. 8 divided by 2. So remember, this is something else we know, that multiplication by a constant carries through. Okay? This is not a product rule in anybody's book. That carries through, and then of course the plus c. And then yes, you would want to clean that up and write that as 4x squared. Yes?
So you wouldn't be able to rewrite the x, like in the first part, you wouldn't be able to put the x squared on top of the numerator, like make it a negative?
Oh, you mean here? I could write it, you mean like this?
Well, yeah, that part. Yeah, you can't put that into the numerator.
Like this? Wait.
Well, like, you know how you usually take the bottom? And
Right,
the
so,
top?
well,
Yeah.
but, so remember what you're doing. If you're doing that, then, oops, then you're multiplying by x to the minus 2. Yeah, you could do that.
Oh, you can do that.
But then you distribute. So now you've got x to the fourth times x to the minus 2, which is x squared. And you have 8x cubed times x to the minus 2. You add those and you get that. So it's a different process doing the same thing. Yeah, that's fine. Yeah. Just those can't cancel, right? Everyone sees that. You can't. So when you're canceling, you can't, if you're going to cancel something, because another way to look at this is, I could take an x squared out of everything, an x squared out of this, and this, and this. If you can take it out of all the terms, then it ends up factoring out as an x squared over x squared, which cancels. So that's another way to think of it. But the important thing is that you have to address all the terms if you're going to do it that way. Okay, so this is one where we've seen this with derivatives, where sometimes you have to go ahead and break apart the fraction to be able to have it in the right form. And then the last bit is true as well, where sometimes we have to multiply out. Here, let me do another one. Yes, I did. I'm a mom, I got mom here. Okay, here's another one. Is there a reverse product rule? No. So what is my only option here? Yeah, I gotta multiply out. And this one's fairly easy, right? I can do that. So let's go ahead and do that. So first, keep your parentheses. Remember, this says take the antiderivative of everything that follows. So you need parentheses to be correct. Outers, inners, lasts. All right, so why don't you guys do the derivative, and I'll do the derivative, and we'll come back and check and see how we match. Oh, and one last thing. When I'm getting ready right now to do the integral, that means I drop the integral sign. You don't keep carrying that along. This is an instruction to do the antiderivative. Once I start doing it, I take that off. So this is what I got. Raise the power, divide by. Raise the power, divide by. Or you can begin to recognize that this is the full derivative of x cubed. So you can just jump straight there knowing that that's a pair. 2x, raise the power, divide by. This is also one of those ones that's an exact derivative. And then, so the integral of 6. Right? What's the antiderivative of 6? Well, 6x, the derivative, remember, you can go back and forth. You can always check your work. That's another important step. So once I get this, if I were to take the derivative, I should get back to what I had inside the integral. So that's always a way to check your work, to make sure that you did it right. So the derivative of 6x is 6, so the antiderivative of 6 is 6x. Or another way, if you want to think about constants, you can write the constant this way, because x to the 0 is, anything to the 0 is 1. So if I write it that way, then I raise the power and divide by, I get 6x. That's another way to think of it. It's just kind of a subset of the power rule. So what do we know? We have 3 basic rules. We have no reverse product, no reverse quotient rule. Do you think we have a reverse chain rule? Yeah. Okay, we'll get to that next time. So if I had something like this, right, you can multiply that out. You can multiply that out, do the antiderivative, no problem. But if you had something like this, you might not want to. Everyone agreed? Yeah. So we have a way to do that. We'll do that next time. So we're not there. Okay, so we've talked about kind of all the different ways to integrate that we know so far. Now let's talk about this. That plus c. Does everyone see why the plus c is there? Does that make sense to everyone? Because whatever I put out here, I could put a 6. Take the derivative, it's gone. 37, take the derivative, it's gone. It could be anything. So these are called general integrals or general antiderivatives because I have no extra information. And a lot of times we do have extra information. And we can use that extra to find what C is. So let's look at a couple of examples of that. So this was general, now we're going to look at specific solutions. And the phrase we use, specific makes sense, but particular solution or particular antiderivatives, that's the kind of the math language. Okay, so this is just where you have more information. So you have extra information, so you can find a value for C. Okay, so here's one. You know that dB dt equals 100 over square root t, and you know that b of 1 is 100. So the idea is to find b. So let's think about what this is. You know the derivative. So this is, again, focus on what you're trying to find. What are you trying to find? You're trying to find b. If I know the derivative and I want to find b, what process do? I know the derivative. I want to work backwards to b, so I'm going to do the antiderivative. So here, oh, that's quite loud. So I want to do the antiderivative. That's how I get, so how do I know that's what I want to do? Because I want to find b, but I have the derivative. So if I take the antiderivative of the derivative is b. All right, so that means I need to take the antiderivative, whatever you do to one side, you have to do to the other side. So I'm going to do the antiderivative here. And so remember, you need to include both pieces. So what's the first thing I need to do? Can I do it the way it stands? I need to rewrite that. All right, so let's rewrite that as t to the minus 1/2 dt. And now it's a power rule. So you guys do yours, I'll do mine. We'll come back and make sure we get the same answer.
Do you not carry through the 100?
What's that?
Do you not carry through the 100? You just...
Oh, I do carry through the 100, thank you. Sorry, yes, thank you. Thank you for pointing that out. I do carry through the 100. So yes, there's 100 stays. And the 100 stays in the numerator where it was. Okay, so give the antiderivative a go. So I'm looking at this as a power rule, so I raise negative 1/2 by 1, so it goes up to positive 1/2. Divide by 1/2 is like multiply by 2, so I get 200t to the 1/2 plus c. Okay, so now, so you can even, if you want to, if it helps you, come over here. This is kind of like when we're trying to find equations of lines. If you use the mx plus b method, it's a good idea to kind of come over at some point and write what you have kind of in one spot. So not the b of t over here and the answer over there. So now what other information do we know? We know that b of 1 is 100. So if I write b of 1, put away the calculator, is 100, what does that tell you? That tells you that t is 1. So go ahead and stick that in. So 200 times 1 to the 1/2 plus c. So I've put in what I know for b and what I know for t. What is 1 to the anything? 1. So now now this is the important part I'm working with. The whole point of this part of the problem is to find c. So I've got 100 equals 200 plus c. I'm going to subtract 200 from both sides. So I'll get 100 minus 200 equals c. So c is minus 100. Remember then to write your final answer. So your final answer is going to be b of t is 200. And you could rewrite that t to the 1/2. It's a little bit easier to think about square root, so if you wanted to rewrite that as square root of t, that's fine. Minus 100, because that's what c is. So, some important things here. When it's written this way, just for a moment, sorry. When it's written this way, and you're trying to find b, that says that you are taking the antiderivative of both sides. You know the derivative, you want the function, antiderivative. It tells you what to do. Do it, and then use your extra information to find c. Is that okay? All right, so let's try another one.
Wait, can you keep that up real quick? Because I couldn't see when you were writing it.
Oh, I'm sorry, yeah, I can tell you what, let me come over here. All right, so here's another kind of problem. What if I say find the equation of the curve that passes through 2, 6, if the slope is given by dy dx equals 3x squared. So what does it mean to find the equation of the curve? What am I trying to find an equation for?
Antiderivative.
I'm trying to find y equals something. I know the derivative, I'm trying to find y, so that tells me I need to do the antiderivative. So here you're trying to find an equation for y. Okay, so find the antiderivative. So y, this one goes to, right over here. Antiderivative of that is y. What's the antiderivative of 3x squared? Yeah, x cubed. Plus c. So I can do the antiderivative. That part's easy. So now, do I have any extra information to find c? Yeah, if this point is on the curve, anytime a point's on the curve, you can substitute it in and it will be true. That's the whole point of being on the curve. So that means I know that when x is 2, y is 6. So I can substitute those values in, just like we do when we're finding y equals mx plus b. If you like the that way of doing it, this is how I'm finding b. So we'll have 6 equals 2 cubed plus c. So c equals minus 2. Is that my final answer? No, I need to actually write the final equation. So the final equation would be y equals x cubed minus 2. Let's check our work. What is the slope of this function? Slope is given by what?
Derivative.
Derivative. So if I take the derivative of this, I get dy dx equals 3x squared. Correct. Does the point 26 lie on this curve? If I put 2 in here for x, I get 8 minus 2 is 6. Yes. So you can always go back and check everything. Okay. And then there's one more that I wanted to do, which is page 330, number 86. Let's see how this works. Let's see. This is for those of you who don't have the book manual. Let's see if that's going to work. Okay. I don't know how well this is going to show up on the video. All right, that's the best I can do, I'm sorry. All right, so if you have your book, it's number 86 on page 330, and it says, the rate of change of monthly sales of a newly released football game, I presume that's a video game, is given by S prime of t. So you're given S prime of t. What What's the first thing we always do when we read a word problem?
Write down what it gives you.
I don't write down what it gives me until I figure out what I'm trying to find. Because that drives, I mean, yes, some people do that. They write down everything that it's given as they read. My suggestion is read through the problem first, figure out what you're trying to find, because that's going to tell you how to organize the information you're going to write down. So if we read through this, we're given S prime, where T is the number of months since the game was released. S of T is the number of games sold each month. Find S of T. So we are trying to find the light keeps going in and out. Find S of T. So now, let's write down what we know. We know it gave us S prime of T is equal to 500 T to the 1/4. And we also know that S of 0 equals 0. So the first thing it says to find S of T, and our secondary question is when will the monthly sales reach 20,000 games? So that's our second question. So find S of T, and when will we get up to 20,000 games? I don't know what keeps blinking. Okay. So if we're trying to find S of T and we know S prime, what do we need to do? Antiderivative, right? If I've got the derivative and I want to go backwards, I need to do the antiderivative. Okay, so S of T on this side, antiderivative on that side. You can write the integral sign if you want to, you don't have to. That's just a reminder of what you're doing. So what would be the antiderivative of this? Is this in the proper form to do it?
Yes.
Yeah, that's a power rule. So we have to raise this exponent by 1, 5/4, and then divide by it or multiply by the reciprocal. I think multiplying by the reciprocal is a little bit easier way to think about it. So 500, reciprocal of 5/4 would be 4/5. And then what else do we need? Plus C. Always have to have a plus C until we find it. All right, so let's clean this up a little bit. So S of T is 400. Everyone sees that's 400 pretty quickly. The 5 cancels with the 500, you get 100. 400 T to the 5/4 plus C. Do we have enough information to find C? Do we have any extra information? Yeah, right up here. This is often called your initial condition. What happens in the very beginning? Where do you stand? So this says, in the very beginning, I have sold no games whatsoever. What else? If we were to write this way, does everyone agree that's also a point? Does everyone agree that's your y-intercept point? Because x is 0. So I could say, I know immediately that C is 0 because it's my y-intercept. Or, the other way to say it is I know S is 0, and I know T is 0. 0 to the anything is 0. So I've got 0 equals 0 plus C, C equals 0. So, yes?
If they give you S of 0 equals 2, it would be just 2.
In this, well, and let me back up for a minute. In this case, because this one starts at 0, 0, because this is a power. So if you were to start with a log function, that wouldn't be true.
Gotcha.
So you have to be a little bit careful. This only works in power situations, not exponential situations, because what is e to the 0? Is that 0? If we had an e to the x in here, e to the 0 is not 0. So the only time that this idea of it being the y-intercept works is when you have a power. Okay, so finally then we have S of T equals 400 T to the 5/4. So now what's our other question? When will we get up to 20,000 games? When questions, what kind of an answer do I give to a when? Yeah, time. So I'm not looking for S, I'm looking for T. So now I want to find T where S is 20,000. So 20,000 games, that's the number of games, that's S. When says find T. So what does that suggest that I need to do then?
20,000 for us.
Yeah, put 20,000 here for S and solve for T. So let's come over here and do that. So we have 20,000 equals 400 T to the 5/4. First thing we'll do is divide by 400. So remember, we're trying to get to t, so we need to start peeling back the layers. And the first layer we're going to peel back is we're going to divide both sides by 400. Is that 50? Okay. Now what do you do? Anybody know how to do that one? You do. You just normally don't think about it when you do square roots. What if I had this? If I had 50 equals t squared, what would you do? Square root both sides. How do I write square root? That's actually also,
4 times the fifth root.
well, close. This would be 50 to the 1/2. Does everyone agree that's true? So when I went from, that's what square rooting is. Yes? All right, so what if I had 50 equals t cubed? What would I do? Take the cube root. Well, another way to write cube root is 1/3. 2 goes to a half, 3 goes to a third. What about fourth? T to the fourth, it would be, it would be the fourth root would be to the 1/4. If you look at what you're doing, this and this are reciprocals. So if I want to undo any power, I raise both sides, well, or you can even think about raising the entire equation to its reciprocal. That's how you do that. So now you've got t to the, because to the 5/4 to the 4/5, when you multiply that out, you get 1, so you'll get 50 to the 4/5. And yes, you may use your calculator. So anytime you have any sort of, I mean, we do this all the time when we do square roots. We just don't think about it this way. So anytime you run into a power, all you have to do is to undo the power is just to raise by the reciprocal. Yeah, so what do we get for a final answer? Anybody do that one? 22.9. Okay, so this is a word problem. We need a word answer. So what is that? Months? Yeah, I think it's in months. And probably you would say about 23 months. That would be fun. Did you get a different answer? Anybody else get a different answer? We'll go with the majority. Okay. All right, so let's look at one last thing. So far what we've been doing is we've been talking about the fact that sometimes you have to rewrite problems just like we did with derivatives. Yes, do you have a question? Did you have a question? Okay, just okay. So sometimes we have to rewrite just like we do with derivatives. You'll either multiply out or bring something up in the denominator to get it in power function form. We know how to find plus c. The last thing I want to look at is a slightly different, it's a slightly different way of writing derivatives. I should say differential equations. So let's look at this one. This is in section 5.3. We're just going to touch a tiny bit on this. So section 5.3 is about exponential decay and growth. Okay, so what if I give you this equation? So far we've had derivatives like this. dB dt equals, what do we have, so 100t, something like that. The variable that I'm doing the integral with respect to is what that is right there. So I could rewrite this like that. So here's a different type though. What if I write this? dq dt equals 7q. This variable and this variable no longer match. Everyone agree that's true? If I'm trying to find q, I still know something about the derivative though, don't I? I know something about the derivative of q. It's just somehow related to q itself. That's typical of exponential relationships. So let me show you what we're going to do. In this case, it would be nice if we had, I'm going to divide both sides by 7. I'm basically going to divide both sides by 7q to get all the q's together on one side. And then I'm going to put the dt on the other side. And actually, I'm going to leave the 7 over here. Sorry. Let me try this again. I'm going to take the Q and put